Dear student, Assalamu alaikum. Hope all of you doing well. In advanced econometrics, today we are going to explore the least square model, the post-estimation test. Learning outcomes. After this lecture, you will be able to understand what are diagnostics tests in regression, that is OLS. There are three types of the test: residual diagnostics test, coefficient diagnostic test, and stability diagnostic test. But in this lecture, we are only explore the residual diagnostic test. The previous couple of lectures, we had explored the methodology of econometrics and least square model along with their important assumptions. In this lecture, we will study the true statistical inference of the least square model. So what are the diagnostic tests? In statistics or econometrics, a regression diagnostic is one of the set of procedures available for regression analysis that seeks to assess the validity of a model in any of a number of different ways. The model fitting is just the first part of the story for regression analysis, since this is all based on certain assumptions. As we know that we will study the different assumptions of the OS model in the previous couple of lectures. The regression diagnostics are used to evaluate the model assumptions and investigate whether or not there are observations with a large, undue influence on the analysis. Again, the assumption for the linear regressions are: there are three important assumptions which we are going to explore today, or violate in case of the violation, how to violate and check the violation of these assumptions. The number one, the normality. For any fixed value of x, y is normally distributed. Serial correlation, it measures the relationship between a variable's current value given its past values. Homoskedasticity, the variance of the residual is the same for any x value of x. So the residual diagnostics. Residual diagnostics include the following test. Number one, the Histogram-Normality test. 1.2, the Breusch-Godfrey serial correlation LM test. 1.3, the Heteroskedasticity test or Breusch-Pagan-Godfrey test. So the starting point is the histogram or the normality test. To check the normality, the first test is the Jarque-Bera test or JB-test. The test is named after the Carlos Jarque and Jarque-Bera. The test statistics is the analysis always non-negative. If it is far from zero, it signals that the data do not have the normal distribution. So Jarque-Bera test, the test statistics of JB is defined as JB is equal to n by 6 into s square plus 1 by 4 into k minus 3 whole square, where n is the number of observation or the degree of freedom in general, s is the sample squareness, and k is the sample kurtosis. The test statistics of the sample squareness and sample kurtosis are given below. So S is equal to mu hat cube and sigma hat cube is equal to 1 over n sum of x minus x bar whole cube over 1 over n summation x minus x bar whole square and whole raised to the power 3 by 2, where k is equal to 1 by n summation x minus x bar raised to the power 4 divided by 1 over n summation x minus x bar square and whole square. What is the hypothesis of the JB test? The null hypothesis and alternate hypothesis are given below. H naught is the sample data are normally distributed, where the alternative hypothesis are the sample data are not normally distributed. What are the practical implications? Are you remembered? The previous lecture we estimate the consumption income regression. Okay. According to this data, by using the Eviews 9, we test our model whether the error term is normally distributed or not. The same rule: if p-value is less than or equal to 0.05, reject H naught, otherwise we fail to reject H naught. And we apply this data to estimate regression. After estimated the regression, we will find the value of JB statistics and p-values. Here the JB is equal to 0.633105 and p-values are 0.728657. So what is happening? Here is a insignificant p-values, that is greater than 0.05. We are unable to reject H naught. This indicates that there is no our data is the normally distributed. So it is also the application and the output of the Eviews 9, the histogram and the value of the Jarque-Bera and probability value indicated that our model is normally distributed. Our next test is Breusch-Godfrey serial correlation LM test. The Breusch-Godfrey serial correlation LM test was named after the econometrician Breusch 1978 and Godfrey 1978 simultaneously published the paper on the serial correlation detection. The Breusch-Godfrey test is a test for the autocorrelation in the errors in our regression model. It makes use of the residual from the model being considered in the regression analysis. And a test statistics is derived from these. The null hypothesis is that there is no serial correlation of any order up to P, because the test is based on the idea of Lagrange multiplier test. It is sometimes referred to as the LM test for the serial correlation as well. The null hypothesis of LM test for the serial correlation: H naught, no serial correlation, and alternatively the serial correlation exists in the model. By using the Eviews 9, we test our model whether the error term is serially correlated or not, or the autocorrelation exists in our model or not. The same rule, same as previously I have explained. If the p-value is less than or equal to 0.05, reject H naught, otherwise we fail to reject H naught. The F statistics of the LM test is 20.077061, where the p-values are highly significant, that is 0.0000, that is the less than 0.05, highly significant. For these p-values, we reject our null hypothesis, that is our model is serially correlated, or the serial correlation, the problem of the serial correlation exists in our model. Remember that these tests only check the problem, not solve the problem. Our next lectures based on how to solve these problems or achieved the true statistical inference. Here is the Eviews output of Breusch-Godfrey serial correlation LM test, F statistics, and their p-values are available. So our next test is the heteroskedasticity test, that is the Breusch-Pagan-Godfrey test. The Breusch-Pagan-Godfrey test, sometimes shortened to the Breusch-Pagan test, is a test for the heteroskedasticity of error Heteroskedasticity means differently scattered. This is opposite to homoskedastic, which means same scatter. Homoskedasticity in regression is an important assumption. If the assumption is violated, you won't be able to use the regression analysis or achieve the true statistical inference. So how to running this test? The test statistics for the Breusch-Pagan-Godfrey test is n times r square with the degree of freedom, where n is equal to sample size and r squares coefficient of determination of the regression squared residual from the original regression. K is the number of the dependent variables. Hypothesis testing. The test statistics approximately follows a chi-square distribution. The null hypothesis for this test is that error variance are all equal. The alternate hypothesis is that error variance are not equal. More specifically, as y increases, the variances increases or decreases. Simply we can say that the H naught, there is equal variance or error terms are homoskedastic. Alternatively, error terms are heteroskedastic. So we estimate this test with the help of Eviews 9. The F statistics we obtain is equal to 0.057484, where the p values are 0.8120. Remember, we are unable to reject the null hypothesis because our p values are greater than 0.05. Okay, what does this mean? This means there is no heteroskedasticity exist in our model because we are unable to reject the null hypothesis, because the null hypothesis is equal to no heteroskedasticity. So here is the Eviews output heteroskedasticity test, Breusch-Pagan-Godfrey test, the F test, and observation into r squared. This is the probability, the chi-square as well. Thank you.